Okay, let's start the second half. So here also we still continuing doing the stress analysis on this system. All right, then first, so the question is, we would like to determine the stress in the members and the connections of the structure shown. Okay, so we would like to know the stress for all of the components. For example, this joint, this pin, and also this pin. Okay, so we would like to know the stress of all of the components. So from the static analysis again, we have this number 40 kilonewton for AB, force in AB, member AB, and 50 kilonewton for member BC as a tensions. So we must consider the maximum normal stress in AB and BC and the shearing stress and the bearing stress at each pin connections. So here is what stress we have to find. Okay. So next, the rod is in the tension of 50 kilonewtons, and the rod center is normal stress. So here, let's change the color. Center it here. Okay, then at the flattened rod end, the smallest cross sections area occur at the pin and the center line. We would like to find the stress in this area. You have tension here. You have tension in these directions. Tension. So in this smallest area here, you will also get the tension here. And how do we find the stress? Also again, the area is equal to 20 millimeters. Okay, this 20 millimeter is the thickness of the rod. Okay, 20 millimeters. So, and next one is we have 40 millimeters minus by 25 millimeters. So this one is from this area. You know that is this 40 subtracted by this diameter. Okay, so we got the area there. And for the force, in here we got 300. Okay, and this BCN is equal to P over A, or force over A area is equal to 167 megapascal. Okay, so here is the stress that we got. And for the boom, okay, the thing is I didn't have picture for the boom, but you can see from previous slide, this one, we have got also the compression stress right there, and the compression stress there is equal to negative 26.7, which is in the compressions. And this is also, you can do it by yourself, this stress, A and B equal to also P over A. Okay, and this P is 40 kilonewtons, and area, you can also take a look there, it's 30 multiplied by 50 meters square. Okay, and then at the end you will get 26.7. Okay, so and so the minimum area section at the boom end are unstressed, and since the boom is in compression, so we don't need to calculate at the end of the boom because this is compressions. So for example, you have a pin like this, right? And then when you got compressions, you can just imagine that in this area there is no stress over there when you are in compressions. Okay, so there is no need to do the calculation over there. Right, then next is the pin stress. So let's have a look for the cross-section area of the pins. So we would like to find the shear stress. You remember when we have a pin like this, and then we have two objects, and this will get, for example, shear stress on the ball or on the pin, for example. Then first we have to find the area for the pin ABC, and the area in this case is pi r square equal to pi 25 millimeters square over okay, this one over 2, because here is the diameters, and then it's equal to 491.6 meters square. Okay, and here we know that we have 50 kilonewton force, and then okay, and then we got the shear stress as P over A equal to 50 times 10 kilonewtons over 491 meters square, and then is equal to 102 megapascal. Okay, then you know that the shear stress there is this number, right? And the pin, next is for the pin A. Pin A is what? We have double shear stress there. Okay, then we got A equal to P over A, and here we reduce the force to 20 kilonewton over A, or over 491 equal to 40.7 megapascal. Right? Then next is this one. This one is quite complicated, this one. So okay, let's see this. I will need to show you where this location is. This location is this one. Okay, and then we have the force. This one is according to the internal force that we already defined here. Here is also external force, 30 kilonewton, remember, and here is 50 kilonewton also. And then from this we can find the force PE, or this is the force, shear force that the pin experience. You can just do the cross sections cut here first. This is one, this is one, and then you know PE is equal to 15 kilonewtons. Okay, then here's the first shear force, and then you cut also here. Okay, then next is, this is 2, then you second cut here, you got this kind of equilibriums, and then if you connect those arrow here, you will get 20, no, this one is 15, 20, and then you know from the triangle rules this is 25. Okay, 15, 20, 25, because this is 3, 4, 5 as a triangle rules. So we know that PG equal to 25 kilonewtons. Then if you cut the third plane, it doesn't matter, because when you cut the third plane, okay, when you cut the third plane, it will be similar to the second one. And when you cut the fourth plane, it will be equal to the first one. So actually you're just doing this to cut, and then it's enough. And then you know that this is the highest shear force, largest shear force. Then you can just do calculation of this shear force by only PG here. This is 25 kilonewtons over 491 equal to 50.9 megapascal. Okay, so here's the stress also in this pin. And then lastly, last but not least, this one we have a pin bearing stress. And this pin bearing stress, you know that we have this, you know, we have to find this area here. So the thickness here is 30, use this thickness, and we use these diameters. The diameter here is 25. Okay, this is for the first one. So this is for this pin. This is for bearing of these objects. Okay, so we have bearing equal to P over T and D, and then here is 40 kilonewtons over 30 millimeters, 25 millimeters from the diameters, and this one is 53.3 megapascal. And another one, this one we will have this, I will say, write this in green. We have this area here. So this is the bearing surface of those area, B equal to P over TD again, and we have 40 kilonewtons, but here we have 50 millimeters because we have 25 here as a thickness, as a width, and the thickness, and then we have 25 also again from these diameters, and in the end we got 22.0 megapascal, right? So this is done for this, all the calculation for the stress, and for each and every stress that we compute here, we have to compare each stress with the strength of those components, because I'm not sure whether everything is in the stainless steel or not. But if suppose we have every component as the stainless as a steel, so we have the strength of 165 megapascal. This is okay. This is okay. This is also okay. This is also okay. The stress, the shear stress here, this is also okay. But here we expect to have a crack on this area because it's 2 megapascal more than the strength. Expected. Okay, so this is just if we assuming that every component is the steel of 165 megapascal strength, right? Then we expect this to break on this hotspot. Okay, so next we would like to learn about the stress into force member. Okay, so when we have force here as a P, and then the axial force on those two members, only a normal stress on the cut plane perpendicular to the member of the axis. So we have a cut plane here perpendicular to the axis, and then if we cut it like that, okay, the transverse force of the ball at the pin resulting in the only shear stress. So if we cut it like this, we will get also we will get also the same force, also P here. So if you cut every sections of those bar, you will get every location of those bar will experience the force P. Okay, and transverse force of the pin resulting in only shear stress at the plane perpendicular to the bolt. So means the shear stress is only happens over here, only there we have a shear stress. Okay, but here we have, but comparing to this one, we have the stress in every inch, every millimeters of this bar, but the shear stress is only one locations. If you move the plane up a little bit up, then you will not get shear stress. Okay, right? And what about the stress on the oblique plane? Means the plane is not really perpendicular to the force we apply. So if we have this force applied on the horizontal, this one like this, but our plane have the angle. Okay, our plane really have the angle. How do we define the stress and the shear? So if it really have this angles, then you say that our force is the perpendicular force. We have to decompose this P onto F and V. If you remember, we did this before, so we can do this, and then we will get what is V here. V is shear, and what is F here? F is normal stress. Okay, then from this we can calculate the normal stress and the shear by this plane like this, but means our stress here will not be as high as the perpendicular. If we have this and then we cut the plane like this, we have force like this, this stress 2 will be more than stress 1, and this is stress 1. Okay, this is stress 2. Means when we cut the plane and have some angles, we will reduce the stress in the plane. Okay, but what is the maximum stress? As I told you, the maximum stress here For the normal is the perpendicular plane. But the maximum shear, okay, sorry, I would like to go back, but I'm struggling. Okay, so here max normal stress plane, and here is max shear stress plane. And then here we have angle equal to 0, but here we have angle equal to 45 or minus 45. Okay? So, please be careful because some materials, they have less shear strength than the normal strength. So means sometimes even though we have shear stress which is lower than normal stress, but some material is tending to breaking by the shear stress more than normal stress, for example. Okay, so the stress under general loadings. Here when we have really a 3D objects here, our stress will also become 3D, and then it depends on the axis here. How do you define the axis? And you can also find the stress and the shear stress by this formula, but on the next following slide will be easier to explain. And here if we say our stress is in the cubics, so this is really small cubic on the bodies, then we have here add a stress in the z-axis, and then here is the normal stress in y-axis, here is normal stress in x-axis, if we consider it in 3D. Okay, so here is the normal stress. And then what I circled in green is the shear stress. For example, this is shear stress by this z-axis, and this is shear stress by y-axis. So that's why they written in tau y, z, and yx. And this is shear stress in s-axis. Okay, so this is how it look like in the 3D world. Okay, and last slide here before I'm going to close this. Actually, if you remember, I did something like this before. Okay, maybe I show this. I say if the strength more than stress is okay, but is it really okay? For example, if our stress is 164 megapascal and our strength, the red zone that we shouldn't touch is 165 megapascal strength, and then here we say stress is this okay? In reality, no. You can imagine when I build a lift, for example the elevators, and then I build the lift here. I have a cable, and this cable I say the strength is 100 megapascal, and we have the load here. One person is 95 megapascal. No. I say one person is 9.5 megapascal, and then I allow 10%. Is it really okay? Really like this? No, because you know there is some uncertainties. Even though you design this to be 100 megapascal, how can you being so exact? For example, the production process of this cable. Are you sure when you produce 1000 of this cable, the strength is 100 megapascal for all? For example, some cable might have 99, some cable may have 98, some cable may have 105, some cable may have 90 megapascal for the strength because of how precise you produce this cable. So this is one reason. So uncertainty of this strength, and the other side is uncertainty of the stress here. How do you know 10% is about 9.5 megapascal? Maybe all of them are really fast. For example, they are doing sumo, and sumo guy get into the lift by 5 people, but maybe the stress is already 150 megapascal. Yeah, so you cannot do it like that. So maybe I just do it quickly. Safety So do you know that the safety factor for elevator, how much it is? What is safety factors? So the structure of the member or the machine must be designed such that the working stress are less than the ultimate strength of the material by these safety factors. Okay, this safety factor Fs is just the strength over the stress. Okay, so in this case it's just, if I say this is 100 over, this is 95 megapascal, and then we say this, our safety factor is about 1.1 for example. Is it enough? No, this 1.1 safety factor is not enough for the safety. For example, for the lift, the safety factor for the lift SF is 11. Means when you know that your allowable stress is 95, when you design the lift, you have to design the lift so that the lift can withstand about 1100 megapascal or more. So it means the strength have to be 11 times more than the stress for safety reasons, because you know when the lift is falling down, you will cause a lot of life. So we need really huge safety margin to prevent this unpredictable incidents. So the factor of the safety factor, considering the uncertainty of material properties, uncertainty of loading, uncertainty of analysis, maybe you analyze it wrong, number of loading cycles, because maybe you are not breaking in one time, but maybe over 10 years your lift is experiencing the load by 10,000 cycles, but maybe it's break in 9,000 cycles, for example. And the time of failure, because maybe this cable here maybe is corroding by the rain or by the oxidizations to the steel, so we have to take care of that also. Maintenance requirements and deterioration effects, importance of the member of the structure integrity, the risk of the life and property. So this is really important. For example, for the lift, we have really huge safety margins. Maybe for the other application, maybe we don't need this high. Maybe it's only 2 or 3 or 1.5 safety margins. But for the lift, it's most likely, as I search it in the internet right now, is 11. Okay. So, and lastly, in the inference of the machine functions. Okay. So that's why in reality, this is not okay. Absolutely not okay. We need some safety margins. Okay. But anyway, don't confuse this. If we have something like this, the exam, you just need to compare the strength more than the stress. But then if I also give you a safety margins, maybe you have to calculate back, is it still okay? For example, if I say the safety margin is 2, SF is equal to 2, then this one is not okay. Okay, because this one safety margin is only 1.1 or 1.0 something. It's not enough, it's less than 2. Alright, then I think it's come to an end of this chapters, and then see you again next time. Thank you very much.